Hello, welcome back to Algebra. In this lesson, we're going to talk about something really important. We're going to talk about the real numbers and the imaginary numbers and bring them together and talk about the concept of what a complex number is. Complex number. And so we're going to talk about complex numbers, and we're also going to talk about the complex plane. Now, a lot of students look at complex numbers when they first learn it, and it looks difficult and hard, but I want to break it down for you here and show you how easy it is to understand what these things really are and how we use them in math, right? But more than that, in the beginning, I want to show you an outline of all of the numbers that we use in math, starting with complex numbers and how it trickles down to all of the real numbers and the integers and all the things that we've been using. So we're going to draw like a hierarchy of all of the numbers so that you understand where they all fit into their place. And you'll understand at the end of it that the complex number is really the most general kind of number that we have in math. It's the granddaddy of all of the numbers. And then the last half of the class, we're going to learn that a complex number can be represented on what we call the complex plane. All right, so we're going to do a hierarchy. So up until now, up until algebra, all of the numbers that you've ever learned in your life are all real numbers, whether they're fractions or decimals or negative numbers or positive numbers, integers, any of those numbers. Those are all real numbers. And then we get to this point in algebra where we learn that we also have these things called imaginary numbers. So the real numbers are just numbers, right? And the imaginary numbers have an I involved. We talked all about that. Now it turns out that there's a more general type of number called a complex number. And that is a number that has a real part, right? A real part of the number, but also has an imaginary part too. So you see all those numbers that you've dealt with, like fractions and decimals and integers, those are really purely real numbers, just a real part. Like 5 potatoes is a purely real number. There's no imaginary part to that. But then we also talked about these imaginary numbers, which more generally we should call them purely imaginary numbers. In other words, 5i, 6i, 7/2 I, those are all purely imaginary because there's no real part of those numbers. Those are pure imaginary numbers over there, and we had the pure real numbers from before. If we join them together so that we have a real part and an imaginary part, then we form the more general number called a complex number. And you're going to learn, you're going to use complex numbers to solve equations from algebra on into more advanced math. They're never going to go away. Complex numbers are the most general number that we have, and they pop up in the solutions of tons of equations in real life. So let's just draw a hierarchy of what these things really are. So we have the idea of what we call a complex number. A complex number. And when we say a complex number, it's any number that has a real part but also an imaginary part. So the real part would be A, for instance. I'm using the letter A to represent the real part. And the imaginary part would be some number B times I. So a purely real number would just be like 5. I'm going to represent that with A. And a pure imaginary number would be whatever, like 5i or 6i. Here I'm just using the letter B, but that's purely imaginary. If you stick them together, you have what we call a complex number. So let's give some examples of complex numbers. The number 4 plus 5i. This is a complex number. Now, the first time you look at this, it looks crazy because you have a plus sign there. And up until now, you're all used to dealing with numbers that is just like a single entity, like 6 or -7, or for imaginary numbers, like 10i or something. So people look at that plus sign and they're like, that's crazy. Why can't I add them together? Why is there a plus sign there? And that is because the real part of the number is 4. The imaginary part of the number is 5, or 5i, right? But if you try to add them together, you really can't do the addition because, as we know, when you add imaginary numbers, you can't add them unless the I is present in both cases. So we say that this number is a more general type of number. It has a real part of it, but it also has an imaginary part of it, right? And since I really can't add them together, I just have to leave the plus sign there. Just like x plus y, I can't really add that together either. So I have to leave it x plus y. So you need to get used to complex numbers having this plus sign here, but really all you need to know is there's a real part, there's an imaginary part. I try to add them, but I can't really do it, so I have to leave it like this. Another example of a complex number would be, for instance, -3 minus 2i. I'll put a little semicolon there to tell you that these are different things. -3 minus 2i. So the real part's -3, and the imaginary part's -2i for this number. Another example would be 6 plus 0 times I. So this is kind of getting into what I was telling you. See, this is the real part of this is 6. The imaginary part is actually 0. So every number that you've ever known, like 5, 6, 7, those are all what we call the real numbers. But really, they're all complex numbers. But they're complex numbers where the imaginary part doesn't exist. So any real number that you have is really a complex number with the imaginary part set to 0. So I'm just showing you that these are complex numbers too. And then another crazy example, you can have, for instance, negative 2 times I times the square root of 3. This is an imaginary number. We call that a purely imaginary number, but it's also a complex number because there's an implied 0 here. There is no real part of this. It's purely imaginary. So the idea of a complex number is it's any number where you have a real part and an imaginary part. The real part sits by itself. The imaginary part is linked by a plus sign, as we have in these first two examples. But of course, I can set the imaginary part equal to 0, or I could set the real part equal to 0, but they're still complex numbers. So really, any number possible is always a complex number, because any number will always be able to be written as a real part and an imaginary part. And you might say, why do I care about this real part, imaginary part? Remember in the last lesson, I gave you examples of how imaginary numbers pop up in applications, in science and math. You just can't get away from them. And I kind of fibbed a little bit. It's not just the imaginary numbers that pop up. It's really the concept of a complex number is what really pops up all the time. So in 3 or 4 years, when you solve a really complicated equation in calculus, you might get a complex answer, right? A real part and an imaginary part. But as we combine these complex numbers together in different functions, we might get a real answer out of the whole thing, as we discussed in the last lesson. We talked about when I talked about imaginary numbers. Sorry about that. So the complex number is the most general thing, all right? And that's why it sits at the top of the food chain. So I'm going to draw a little box around this. So underneath the idea of a complex number is what we talked about. We have the real numbers and we have the imaginary numbers. They are what live as children under the granddaddy, which is the complex number. That encompasses everything. So under here, let me go and draw a little arrow down because it lives kind of underneath here. Underneath complex number, and on the other board we'll do the other side, we have what we call the pure imaginary numbers. Numbers. Pure imaginary. Those are numbers with just I, right? And so what kind of examples would that be? Well, it's going to be, for instance, a plus bi, which is a general form of a complex number, however, with a set to 0 and b not equal to 0. In other words, it's a complex number, but where we set the real part to 0, and then this part is non-zero. So to give you some examples of that, some concrete examples, we know what these guys are. These are just the imaginary numbers. 3i, that's a purely imaginary number. Negative 2i, that's a purely imaginary number. 1/2 I, that's a purely imaginary number. So you can have fractions, of course, involved. I times the square root of 3, that's a pure imaginary number. Don't let the square root get in your way. I mean, it's still just an imaginary number, right? Of course, let's go down below here. We could have negative something crazy, 2i times the square root of 7. So any number, radicals, negative, positive, fractions, doesn't matter. If you have an I and it's just purely imaginary, we call that, obviously, the purely imaginary number. So let me draw a box around all of this stuff. All right? So if this describes what lives under the complex number, one subset of complex numbers are the purely imaginary numbers, and the other subset are going to be the purely real numbers. So we're going to go over and draw a little arrow this way, and I'm going to kind of continue it here. Let me see how I'm going to do this. Yeah, let me go right over here. Let me go way over to the center of the board. I'll come down right here, and I'm going to show the other half of what lives under a complex number. We call these pure real numbers. Actually, you don't even need the word pure. They're just real numbers, right? So what would that look like? Well, it's going to look like the general form of a complex number, a plus bi, but b is going to equal to 0, and a is going to not equal to 0. So in other words, it's a complex number where there's no imaginary part, only a real part. That's why we call it a purely real number, or just a real number. All right, so what are examples of real numbers? Now, when I say real numbers, it's literally anything on the number line. Any number, integers, non-integers, fractions, decimals, whatever. As long as it lives on that real line, it's called a real number, right? So it's literally anything you can think of as far as like basic numbers. So for instance, the number 6, that's a real number. The number square root of 2, that's a crazy radical, that's a real number. The number 2 pi. Pi goes on forever as far as the decimal places, but it's still a real number. It lives on the number line. Negative numbers are totally fine. That live on the number line. So like -1/2. Fractions are totally fine too. -4, that's a negative whole number or negative integer on the number line. And let's go down here and say, let's say 2.62 with a bar over the 2. You see, this is 2.62222222222 that repeats forever, right? So if it repeats forever, if it doesn't repeat if this guy is a repeating decimal, or if it's like square root of 2 or pi where the decimals never repeat, so this is basically rational or irrational, it doesn't matter. Everything is contained under the umbrella of a real number. If it lives on the number line, whether or not it's a repeating decimal or not, whatever, negative, positive, basically it's a real number. So you see what we have is the complex numbers are the granddaddy because they contain real and imaginary parts. But as a subset of the complex numbers, we have just the real part, which is pretty much any number you can think of on the number line. And then we have the pure imaginary parts, which are any number that would live on kind of like the imaginary number line, which we'll talk about in a minute. But pretty much fractions, decimals, negative, positive, whatever, as long as there's an I in there, it's a purely imaginary number. Now let's go a step further. Let's take a look at what lives under the real numbers. Real numbers are in general broken up into two parts, right? We have the rational numbers, which can be written as fractions, and we have the irrational numbers. Those are the two general kinds of real numbers we can have. Because all numbers that live on the number line can either be written as a fraction or not written as a fraction. So those are the rational and the irrational. So we have two categories. So the first one is called rational numbers. And I know you've all heard about rational numbers. We've discussed it many times ourselves in this class. The rational numbers can be written as fractions. The number 6 can be written as a rational number because it can be written as 6/1, which is a fraction, right? Of course, the number -3/4 is a fraction itself. Negative doesn't matter. If it can be written as a fraction, it's still a rational number. What about certain decimals? Let's look at 1.25. Well, you might say, well, that's not a fraction, but I can write this as a fraction. I can go in a calculator and figure out something divided by something to give me 1.25. And then as a final example, let's say -6.27 with a repeating decimal bar over the 27. So this is -6.27272727272727, right? So the basic idea here is, let me circle this and then we'll get back to it. So what live under the real numbers are the rational numbers, and then we're going to talk in just a second about the irrational numbers. So it's obvious that this is a rational number because it can be written as a fraction. It's obvious that this is because it's a fraction. These two trip students up. Basically, if a decimal can be written, if a decimal is truncated like 1.25 or 3.75, then you can always write it as a fraction, always. That's something you learn as you kind of work through the problems. Anytime it's a truncated decimal that stops, it can always be written as a fraction, so they're all rational. Also, if a decimal goes on and on forever, even if it goes on and on and on forever, but in a repeating way, like 22222, that's a repeating pattern, or 272727 forever, or 399, 399, 399, 399, if it repeats in any pattern forever and ever, then it can always be written as a fraction, so it's rational. But the flip side of this is we have other numbers that are not rational, and we call those irrational numbers. And I know that you know what these are. We've talked about them before. They're the very special numbers that cannot be written as a fraction, right? So those are numbers like pi. No matter what anyone has ever told you, you cannot write pi as a fraction. And when I say written as a fraction, I mean written as a ratio of whole numbers, like 3 and 4 and those kinds of numbers. That when I say written as a fraction, that's what I mean. All right? The number -pi/4. Pi itself is irrational, so of course pi/4 is also irrational. The number -√2. If you actually take square root of 2 and calculate what it is, there's no repeating pattern to the decimal. The decimal just goes on and on and on forever. Some more examples. The cubed root of 5, that's irrational. And the number e, which we're going to talk about later when we talk about logarithms and exponential equations, e is a special number. It's about 2.71, but it has a decimal that goes on and on forever. It never ends, and there's also no pattern to the decimal. So the basic idea is irrational numbers cannot be written as fractions because they have decimals that go on forever with no pattern. So if there's no pattern to the decimals that go on and on forever, then there's no way to write it as a fraction. Whereas these, if they have truncated decimals or decimals that go on forever with a pattern, you can write them like this in terms of a fraction. So we call them rational. So these are the two main kinds of numbers that live underneath the concept of the real numbers. That's pretty much all the numbers that can live on the number line. Either they can be written as a fraction or they cannot be written as a fraction because the decimals go on and on forever with no pattern. Notice negative, positive, fraction, all that stuff is, or negative, positive is okay. It's just the decimal repeating nature of it determines if it can be written as a fraction or not. So that's the end of the road for the irrational numbers, but we still can break down the rational numbers a little bit more if we want to, right? So I'm going to go here and I'm going to draw another branch right here. So underneath the rational numbers, you can have the fractions and you can also have the integers. That's kind of how we can break that up some more. So we have fractions, right? What are some examples of fractions? I know that you all know what fractions are, but you know, we have things like 1/2, that's a fraction. We have 3/4, negative 3/4, negative, positive, doesn't matter, it's a fraction. 6/13, that's a fraction. So of course that's 1/2 of the types of things that can live under the rational number umbrella, the fractions. But we also have the integers, right? Because we say 6 is a rational number also. It can be written as 6/1, but obviously it's different than the fraction. So we can have the fractions, we can also have the integers. So what we can do is, let me come down here and say, well, let's go down here and let's break this into integers. What are integers? Well, integers are basically whole numbers, negative and positive kind of whole numbers that live on the number line and including the number 0. So for instance, -6 is an integer, you know that. -2 is an integer. 0 actually is an integer. And the number 4 is an integer. The number 17 is an integer. So you see, they're basically whole numbers, including 0, but they can be negative and positive. We call those integers. All right? And then we're going to box that up. We're almost done with this. And then we'll move along. But underneath the integers, what can live under this? Well, under this, we have the negative integers, we have the positive integers, and then we have the very special number called 0, which is kind of in the middle. So you can break that up into those three cases. So let's go over here, and we have the negative integers, right? And we have the very special number 0. And we have the positive ones other than 0, like 1, 2, 3, 4, 5, 6, 7, 8, 9, those things. We have a special name for those. Those are called the natural numbers. So let's just write a couple of quick examples to show what these are. The negative integers, as you might guess, would be things like -5, -2, -1, -34, whatever. 0 is a very special number. It's the only one that lives right there. And the natural number is everything left over on the positive side. 1, 2, 3, 4, ... Basically the positive kind of whole numbers over there. So we're going to circle this, right? And we're going to circle this guy. And we're going to circle this guy. And we have kind of a special name for 0 and the natural numbers. They kind of can be, you probably heard of the term whole numbers. Because these are the numbers that are kind of like the counting numbers, including, and you also have 0 there. So this is the general idea. Why did I spend all the time to put this on the board? Because I want you to understand the hierarchy of how important a complex number is. You know, you learn when you're a kid how to count on your fingers. Those are the natural numbers. And then you're introduced to the concept of 0, which is nothing at all, right? It's not really something you can count, but it's a concept that we learn when we're really young. We call these the whole numbers, but they're really two different things. These are the counting numbers that we can count. Then we have, of course, 0. Then you learn the concept of the negative number, which is really weird when you first learn it, but we learn about that as being kind of like when I owe you something. You know, that's what a negative number is. Those all fall under the umbrella of what we call integers, which is 0, the positive whole numbers, and the negative whole numbers, right? But integers are only half the story of the rational numbers. We have integers and we also have fractions. You'll learn about fractions, which are basically parts of the integers, essentially fractional parts of the integers. Together, they make up the concept of a rational number, which are basically any number that can be written as a fraction. And then, of course, you have the irrational numbers, which can't be written as fractions. Those are involved in special numbers like pi, square roots of numbers, cube roots of certain numbers, e, and things like that. Decimals that never ever repeat in a pattern. And then those live under the umbrella of the real number. So all of these numbers from here down live on a number line somewhere with a purely real part. You see here's an irrational number, here's an irrational number, and all the other ones are rational, but they all live under the number line. And then we've learned now in algebra the imaginary numbers, which are totally separate ball of wax, numbers that exist on a totally different number line, and they have their own kind of life over there, but they fall under the general umbrella of what we call a complex number. So the complex number lives at the very tippy top of the pyramid. It literally is all of the possible numbers that we know to exist. And so we use them to solve equations. They have very practical applications, but that's generally the idea of what a complex number is. And a complex number will always have a real part, and a complex number will always have an imaginary part, and denoted by the I. So now we want to talk about this thing called the complex plane. A lot of books will just throw you into the complex plane and say, here it is, enjoy it, and it kind of gives students a little bit of heartburn. So I want to break it up and take it just a tiny bit slower so you really understand what the complex plane is. So here we have this thing called complex numbers. I want you to kind of keep that in the back of your mind, kind of like just think we're going to get back to it, but just keep it in the back of your mind. First, I want to talk about something you know more about, the purely real numbers. You know about purely real numbers. We've been using them forever and ever. All right, so let's talk about that for a second. We have real numbers. Numbers can be graphed on number line. Right? A regular old number line, nothing fancy, nothing crazy, right? So let's do that real quick. Let's just draw a quick little number line here. Go down memory lane. We did these a long time ago. We say 0 exists here. And let me put a tick mark here, tick mark here, tick mark here, couple tick marks here. Now, because we're talking about real numbers, you all know that this number line is real numbers, but I'm just going to put the word or the little letters RE over here just to remind you that this is really, we're just talking about the real numbers. This is, numbers that we've been dealing with all of our life. But the point is you can graph numbers on the number line. Any real number can be graphed on the number line. So for instance, the number 1, we can just put it right there and say it lives right there in the number line. Right? The number 3 is a real number. We can just say it lives right there in the number line. The number -2 exists right there. We say it lives on the number line. Of course, the number 0 is on the number line. And then, of course, all the fractions and everything else can live there, too. We can say this is 1/2. It exists on the number line. If I want to put pi on the number line, it's going to be 3.14. It'll live a little bit to the right of 3. Square root of 2 is on here. 1.41 is square root of 2. It'll live around here. You get the idea. No matter what number you want to plot on the number line, you just draw the horizontal number line, tick marks, and then you put the point on that line anywhere you want. It is going to find a home somewhere on this line, every real number that you know about. All right, but then we have the idea of the imaginary numbers. So we have this idea of imaginary numbers. We know that that's going to come into play some sort of way. But here's the deal. If we start plotting all of the imaginary numbers on this same graph, it's going to get really confusing. Because if I start plotting the number 1 and then also the number 2i on the same exact number line, I mean, you could do it, but then you're going to get really confused as to which numbers on that line are real and which numbers on that line are imaginary. But we would like to plot the imaginary numbers, so what do? So what we do is we graph the imaginary numbers on a vertical line. In other words, we just turn the line sideways. So instead of doing it horizontal, we draw a totally separate line, like this. Why do we draw it up and down? Well, we want it to look different than this one because we're going to end up writing the imaginary numbers. So we're going to put the word IM there to remind me that what I am actually plotting here is imaginary numbers. So here I have my 0 point on this, okay? And I can put tick marks on this line just like I have tick marks here. But you see, if I want to plot numbers on this line, they have to be, of course, imaginary, right? So let's plot a couple of numbers. So here's 1, 2. But this is not 2. This point is not 2. This point is 2i, because this is not a number line with real numbers. It's a number line only of imaginary numbers. And this is not the number 2. This is number 2i, right? And then, of course, you could say -1, -2, -3, -4. Here's a point. Let's just plot it right here. What's this? It's not -4. It's -4i, right? And then, of course, I can plot something in between 0 and 1 here. And this would be -1/2, but it's not -1/2, it's -1/2i. You see the idea? This point right here is not the number 3, it's 3i. So we have the idea that if you have purely real numbers, you just plot them on a horizontal number line like this. And if you have purely imaginary numbers, you just plot them on a vertical bar like this. We use the word RE to tell me I'm only plotting real numbers here. We don't need to do that when you're in basic math, but now that we're here, we need to show what we're plotting. And then we use the letter IM to tell me that I'm only plotting imaginary numbers. And when I plot the number, I need to make sure and put the I's here to remind me that I'm not just plotting real numbers, I'm plotting imaginary numbers, right? So then, if we know how to plot the real numbers here, and we know how to plot the imaginary numbers here, how do we plot complex numbers? Because complex numbers have a real part, but they also have an imaginary part. So here's the punchline of the whole thing. We use a vertical line and a horizontal line to form a plane. We call it the complex plane. And all of the complex numbers live in the complex plane and can be plotted on the complex plane. So here's your handy dandy complex plane right here. Notice that we have a real axis. All of the purely real numbers that you want to plot in your entire life that you've ever done, you just plot them on this real axis down here, right? So in previous math classes, you didn't even know about the imaginary axis, so you just poof, disappear it, and you only look at this right here. But now we know about imaginary numbers. So the purely imaginary numbers are plotted purely on this axis right here, just as we have done, because they only have imaginary parts. But as you now know, the complex numbers have real parts and imaginary parts. So what we're going to do is we're going to plot a few imaginary numbers. So let's go ahead and do that. What would, let's just pick something. Let's take something easy right here. So we have 1, 2, let's put a plot, let's do it in a different color. What would this point be right here? Here's a point right here. Well, the real part is this, so there is no real part at all, but the imaginary part is 3i. So the way you would write this down is you would say this complex number is 0 plus 3i. Because it has a real part and an imaginary part, that makes it a complex number. The real part is just 0. So it's a purely imaginary thing that lives right there. All right. What would this point be right here? Let's go up here. What would this point be right here? Well, the real part is -1. And the imaginary part is 4. So really what I would put is -1 plus 4i. -1 plus 4i. This is the complex number that's associated with this point right here. So cranking right along, what would a number over here be? Let's go ahead and do a dot right here. The real part is -3, so I have -3, but the imaginary part is actually 0 because there is no imaginary part because it's living right there in the axis. So this is -3 plus 0i. What would this point right here be? Well, it's got a real part of 3, and it's got an imaginary part of just a positive 1i. So this is going to be 3 plus I, or 3 plus 1i, however you want to look at it. What about this one on the axis down here? Well, it's got a real part of 2, and it doesn't have any imaginary part at all. So this is going to be 2 plus 0i, like this. That's what that's equal to. Now let's go and plot some down here and see what they look like. What if we go way down here and put a point down here? What does that point signify down there? Well, the real part is nothing, and the imaginary part's -4. So it's 0 plus, well, you say 0 plus a -4, but really you want to write it as 0 minus 4i. You would write it as 0 minus 4i. And then let's say if we do this, let's point right here. Positive real part of 1 and -2i in the imaginary part means 1 minus 2i, the real part being 1, the imaginary part being the -2i, and then the last one I'm going to do is going to be this one right here. The real part's -1, but the imaginary part's -2i. So it'll be -1 minus 2i. -1 minus 2i. So let me just double check myself. So this point is -1 plus 4i, that's good. This one is 0 plus 3i, that's good. This one is 3 plus +1i, that's good. This one's 2 plus 0i, that's good. This one's -3 plus 0i, that's good. This is -1 minus 2i, that's good. This is +1 minus 2i, that's good. And this is 0 in the real part, -4i for the imaginary part. So there you go. That's the idea of a complex plane. Now, when students first learn a complex plane, it looks crazy. How can you have a number that lives on the plane? I mean, a lot of you already know that we use XY planes to represent, points on a plane all the time. But I want you to be really careful, though, because in the past, when I told you to plot the point x comma y, what you're doing is you're basically looking at the inputs of a function, x, and the outputs coming out of the function, we call it y, or you can think of it as f of x, right? So x and y, but the x is the input value of a number, of a function, and the output is y. And we do plot them as coordinate pairs on a graph just like this, but that is different than what this is, because that is plotting input versus output, and you're basically plotting what the function looks like as a function of input and output, input to the mathematical machine of the function, and the output that comes out the other side. That's what we usually are plotting on the XY graph. But here we're not plotting any inputs or outputs. We're saying that these numbers actually have two pieces to them. They have a real piece and an imaginary piece, and there's no way that you can draw those on a single number line because they have two parts. So we have to draw two totally separate axes. So before you learn about imaginary numbers, the only number line you know about is this one, the real one, right? But then when you do learn about imaginary numbers, you learn that there's another number line called the imaginary number line. All the imaginary numbers live on here. But any number that's not purely real or purely imaginary will live somewhere else on this plane. So this thing is not an input-output of a function going on. This is literally saying these complex numbers have two parts that we have to represent. So we write them in what we call the complex plane. Now, graphing them behaves exactly the same as graphing any XY pair. I mean, I've tried to show you here, so it's not magical, but that's what it is. It's really showing you that these numbers have kind of two dimensions to them. You can think of it that way. They have two dimensions. A real and an imaginary part means they have two dimensions. All right? So that's all I really want to talk about now. We introduced the concept of a complex number, how all of the numbers are related to one another. So that's really it. There's no more numbers that we know about. And that's what we have, the hierarchy of the complex numbers. And then we talked about the complex plane. And you're going to be dealing with this later in algebra, but you'll be dealing with it even more in advanced pre-calculus, calculus, advanced calculus, and things like that. Because the complex numbers really are something we use to solve real equations for real applications in science and engineering. So make sure you understand this. Follow me on to the next lesson. We're going to learn how to simplify expressions that involve complex numbers to wrap up this concept in algebra.